Hi there. So today what I'm going to talk about are normal distributions, and you'll see a couple examples of some graphs right here on the board. Okay, the distribution of a data set measures the frequency at which each data point appears. So you might recall the histograms that we looked at in a previous section. Those are a way that we can look and visualize what the data is distributed and how it's distributed. So when we look at each of these graphs, essentially the height of the graph tells us how frequently each of these data points are occurring. Now, there's some important features in normal distributions, and you can look in your textbook and actually see some more precise examples of some graphs. But there's some important features that I want to point out. One of the things is you've probably come across these before if you've heard of bell-shaped curves. Okay? And this is essentially the characteristic of what normally distributed data looks like. So, some important features. One important feature is that the mean is equal to the median, which is equal to the mode. That's a huge statement, okay? So essentially what we're saying is the peak lies directly above the mean. In other words, so right about here is our mean. In other words, our average value is not only the middle value, which means it's equal to the median, but it's also the most frequently occurring data point, which is equal to the mode. Okay? Another common feature is that most of the data is clustered about the mean. And that the bell curve is symmetric about the mean. And one more, the area under the curve is 1. Okay, so notice here. The high point of our graph is all about the mean. It's all real close to the mean, and the further you get away from the mean in either direction, the frequency goes down. Okay? Now, the fact that it's symmetric is what I alluded to before. Not only is our mean our middle value, but one side of the graph, essentially, if I was to draw a vertical line here, one side of the bell curve is a mirror image of the other side. Essentially, so since this is the middle point, that tells us that half of our data is greater than the mean and half of our data is less than the mean. All right, and finally, no matter what these curves look like, whether they're real tall and slim or whether they're a little more spread out, the area under the graph is 1. Okay? Now, a couple things that I'm going to point out here is it turns out that for a normal distribution, the shape of the bell curve is completely determined by two things. It's determined by the mean as well as the standard deviation. Okay? Remember, the mean is the measure of the central tendency. Okay, that's your average value. And the standard deviation tells you how spread out your data is. Okay, so why? Well, notice that the mean tells you exactly where the center of your bell curve is. Okay, that's what the mean gives us. And the standard deviation essentially tells us how steep the curve is. Okay, why? Because if you have a small standard deviation, doesn't that tell you that your data is very clustered about the mean? Well, if your data is very clustered about the mean, what you're going to have is a very tall, thin curve, because most of your data is right in here. Whereas with this normal distribution, our standard deviation isn't quite as large. Notice that your data is a lot more spread out here. Okay, so the standard deviation essentially tells you how your bell curve is shaped. Now, there's a lot of really cool things about data that is normally distributed. One really neat thing that I'm going to share with you is the following rule of thumb. So if a data set can be modeled by a normal distribution, I mean, obviously in quote unquote real life, nothing falls perfectly like this, but it turns out that a lot of things can actually be modeled very, very accurately using a normal distribution. And it turns out that if a data set is normally distributed, approximately 68% of the data lies within one standard deviation of the mean. 95% of the data lies within two standard deviations of the mean. And finally, 99.7% of the data lies within three standard deviations of the mean. Now, this is a general rule of thumb, okay? So let me show you what I'm talking about. We'll just look at our top graph here, okay? What we're saying is, with your mean, what you do is you add on one standard deviation. So take your mean plus a standard deviation and your mean minus a standard deviation. And what we're saying is about 68% of your data falls within this range. In other words, about 34% lies above and 34% lies below. Now, 95% of your data lies within two standard deviations of your mean. In other words, you take your mean and add on 2 times your standard deviation, and you take your mean and subtract off 2 times your standard deviation. And finally, and this is huge, what we're saying here is that all but 0.3%, so 99.7% of the data falls within 3 standard deviations of the mean. So virtually all of your data is going to be within that interval. Okay? So let's take an example and work through it. So let us suppose that the heights of adult males, adult U.S. males, are normally distributed and suppose the mean is 69.1 inches with a standard deviation of 2.65 inches. And what we're going to do is we're going to discuss what does the 68-95 99.7 rule tell us about the heights of the men. Okay? So, what we can say is as follows. Assuming that this is an accurate measure, what we can say is that 68% of U.S. males are between, well, you take your mean, 69.1, and add your standard deviation, and then subtract your standard deviation. So what we're saying here is that approximately 68% of U.S. males are between 66.45 inches and 71.75 inches. 68% of men have heights in that interval. Next, we can say that 95% of U.S. males, well, now what we do is we take our mean and add and subtract 2 times our standard deviation. So this tells us that 95% of U.S. males have heights between 63.8 inches and 74.4 inches. And last but not least, we can say that 99.7% of U.S. males have heights within 3 standard deviations of the mean. So how do you compute that? Literally, you take your mean and add and subtract 3 times your standard deviation. So I'm going to write this in interval notation. What we have then is that 99.7% of U.S. males have heights in this interval between 61.15 inches and 77.05 inches. That's pretty cool, okay? Now, it turns out that normal distributions come up a ton. Okay, they come up when we're talking about weights of newborn babies. When we're talking about heights, they use normal distributions to approximate IQs. Normal distributions if you have a machine that fills up cereal boxes and you want to look at the weights of the cereal boxes. If you look at enough cereal boxes, it turns out that those weights are normally distributed. Now, are they precisely 68, 95, 99.7 with that data distribution? Of course not. What we're talking about is a general model. Now, you may or may not recall, but in our last video, we were talking about z-scores. And in a normal distribution, a z-score for a data point measures how many standard deviations you are above or below the mean. So let me have you recall when we were talking about z-scores related to our standard deviations here. So in a normal distribution, the z-score for a data point gives the number of standard deviations that the point lies either above or below the mean. My hope is that you recall the formula. Z equals x minus mu over sigma. Okay, so this is definitely a unit of measure that we use here. So let me give you an example of how we can apply this to our normal distributions. Suppose there's a type of steer, and the mean weight for these steers is 1,152 pounds with a standard deviation of 84 pounds. So steer A, and suppose there's another breed of steers, we'll call them steer B, and they have a mean weight of 1,300 pounds with a standard deviation of 110 pounds. All right, now when we're dealing with our normal distributions, you need to be told that the data can be approximated by a normal distribution. That's not something in our course that you're going to have to wonder about. You need to be told this is something that can be approximated by a normal distribution, and more often than not, you'll be given your mean and your standard deviation as well. All right, so suppose we randomly come upon a steer breed A that weighs 1,300 pounds. And suppose we randomly come on a steer B that weighs 1,450 pounds. Now clearly, the one that weighs 1,450 pounds is heavier than the one that weighs 1,300 pounds. But again, when we want to talk about measuring two different things that are scaled differently, what we do is we look at their z-score. Again, what we're doing is we're essentially standardizing these so that we can have the measures be equivalent so that we can make comparisons. Something else from the previous video is the one that's further from your mean. In other words, that has either the higher z-score, if it's above the mean, or lower z-score if it's below the mean, is the one that's deemed to be more unusual. Again, why? Because remember the 68, 95, 99, 7 rule. Most of your data is considered to be clustered about the mean. So, how can we determine which one of these is more unusual? What we'll do is we'll compute the z-scores for both of them. Okay, so my z-score, remember, you take your data points, so 1,300 minus your mean, and then you divide that by your standard deviation. And if you do this computation, I did it ahead of time, we get 1.76. So this is nearly 2 standard deviations above the mean. Pretty unusual. Okay, now for this other steer, what do we have? Well, now our data point is 1,450. You subtract off your mean and divide by your standard deviation. And here you're going to get 1.36. So again, this guy can be considered pretty unusual. Which one is considered more unusual, or which one is heavier with respect to its particular distribution? This one here. Okay? Now, also with our normal distributions, another thing that we're going to want to be doing is finding the probability that our data points fall within certain ranges. Okay, so I'm going to attempt to draw a bell curve. Sorry, it's not going to be symmetric. I almost never freestyle these things very well. Okay, so let's pretend that this is a symmetric distribution, and right smack dab in the middle is our mean. Okay, now a couple things to remind you of. One of them is that the area under the curve is 1. And it turns out, and this is super cool, it turns out that with normal distributions, to find the probability a data point lies in a particular interval, all you need to do is find that area. So to find the probability a data point lies in a particular interval, what you need to do is find the area under the curve in that interval. Now, technically speaking, to find the area under a curve, we use our calculus for that. We don't need to do that here. There's tables that can help you compute your normal distributions, and our calculators are really handy tools as well. So for example, suppose this is some point A and this is some point B. And I want to find the probability that my data point lives in this interval. Okay, the way I would write that is I want to find the probability. I'll call my data point X, and I want him to lay between A and B. So the probability that my data point lies in that interval is precisely the area under the curve of this interval. Okay? So, one of the things that I need to go back and remind you of is as follows. We have that interval notation, and I used it over here when we were doing the 99.7 rule with the heights of men. Okay? Remember, back in algebra, when you were looking at your number line, the way you would write an interval, say from A to B, is you would have your parentheses. We always have our smaller number on the left and the larger number on the right. Okay, this is essentially saying X is between A and B. Now, what if we're interested in this interval? Okay, in other words, we're interested in X being greater than A. Well, then the smallest it can be is A, and it goes off to positive infinity. Well, you can't put infinity in a calculator. Infinity is not a number, it's an idea. So what we do is we put a sufficiently large number, and the standard operating procedure that we use is, instead of saying that it goes off to infinity, for our upper bound, we put in 10 to the 99th power. You'll see where this comes in momentarily. Now, on the other hand, suppose I'm interested in X being less than A. Well, there's my value of A, and now I'm going off to negative infinity. So in interval notation, we would write it this way. Again, the larger always goes to the right. Okay, so here my upper bound would be A. What do we put for our lower bound? Well, just as with positive infinity, we put 10 to the 99th. When we have negative infinity, we put negative 10 to the 99th. All right, so what I'm going to show you is how to enter these sorts of things into your calculator, and then we're going to play with some probabilities here. So when you want to find the probability for a normal distribution, okay, what you do is you use the calculator function Normalcdf, okay, because it's a continuous curve and we're looking at a normal distribution. The order in which you put the numbers into your calculator, so you put your lower bound, your upper bound, notice lower is always on the left, then you put in your mean, and then your standard deviation. Okay? We'll practice this in just a moment. Now, if we're dealing with a strictly more than some value, in other words, X is greater than A, then for the upper bound, you would put in 10 to the 99th. If we're interested in it being less than some value, so X is less than A, then for the lower bound, you put negative 10 to the 99th power. Okay, this will help us find our probabilities. And again, you can use a table. I really enjoy using tables because it gives you a nice visual. But the fact of the matter is our calculators also are quite handy. So let me take an example here. Suppose we're going to keep talking about Angus steers. The Virginia Cooperative Extension reports that the mean weight of yearling Angus steers is 1,152 pounds with a standard deviation of 84 pounds. And we're going to assume that these weights can be described by a normal model. So we can use a normal distribution in order to approximate these. All right, so notice we're given the fact that it's a normal distribution, we're given the mean, and we're given the standard deviation. So let's find a few probabilities. Let's find the probability that a randomly selected steer okay, so we're going to do 3 of these. Let's say weighs between 950 and 1,050 pounds. All right, so again, assume this is a decent graph. My mean is 1,152. And right now we want to find the probability that a randomly selected steer lies in this interval right there. Okay? So, how do we make such a computation? Again, you can use your table, or we can use our calculator, Normalcdf. Okay, notice our lower bound. Well, the smallest we're interested in him being is 950 pounds. The upper bound is 1,050. Our mean is 1,152. And our standard deviation is 84. Okay? Now, how do you get to this in your calculator? It's very similar to the way we got to our binomial distribution. In order to get here, you hit second vars, and then you go down to Normalcdf. Okay? And if you compute this and round it to 2 decimal places, about 0.10. So, the probability a randomly selected yearling Angus steer will weigh in that interval is about 0.1. Or about, we can otherwise equivalently say about 10% of all such steers weigh in that interval. All right, now let's find the probability that a randomly selected steer weighs less than 1,250 pounds. All right, well, I'm going to erase these numbers. And now we've got 1,250, and we want it to be less. That means to the left. Now, intuitively, we can look at this and say we know it's going to be greater than 50%. Why? Because remember, half of your data is above the mean and half your data is below the mean. And notice we're starting above the mean and we're going all the way to the left. Okay? I always like to try to think about what to expect just to be sure I don't make a typo in my calculator or look at the table incorrectly. So again, we want to find the probability. So we're going to use Normalcdf. Now, we want it to weigh less than 1,250. So it starts here and it goes down to negative infinity. Now I will grant you that 0 is going to be a lower bound in reality terms, but for standard operating procedures and precision with our measurements, we always go down to negative 10 to the 99th. Again, if you actually put 0 in as a lower bound in your calculator with the number of significant figures we're using, you wouldn't see a difference. Our upper bound is 1,250, and then you put in your mean and your standard deviation. And to 2 decimal places, you'll see that we get 0.88. So we can expect about 88% of our steers to weigh less than 1,250 pounds. All right, let's do one more of these. But now, let's have this guy weighs more than, how about, let's just do 1,200 pounds. And then we've done one of each of these. Okay, how do we do this? Again, the same way, normal CDF. If it's going to weigh more than 1,200, that means 1,200 is our lower bound. Okay, how do we say that it goes off to infinity? Well, again, it goes without bound, so we say 10 to the 99th. And then we enter our mean and our standard deviation. Now, in terms of a picture of how that looks, okay, what are we looking at here now? We want it to weigh more than 1,200 pounds, so that's about right here. So it's certainly going to be less than half. And if we do this computation, assuming we can type it into our calculator correctly, so 1,200 and then 10 to the 99th, 1,152 and 84, we're going to get rounded to 2 decimal places about 0.28. All right, so what have we done so far? Well, what we've done is we've said, hey, this can be approximated by a normal distribution. Here is our mean. Here is our standard deviation. And what we've been doing then is finding the probability that a randomly selected steer weighs within a certain range. In other words, haven't we been given the weights and we want to find the probability or the area? Remember, those are equivalent here. Okay, so with this normal CDF business, essentially what's happening, we're given the data points, and what we want to do is find the probability or the area that it falls within a certain range. Okay, now what I would like to do is contrast that. We're still going to be talking about these yearling Angus steers, but now what I want to know is as follows. What is the minimum weight a steer would need to be in order to place in, let's say, the top 15% of all such steers? In other words, only 15% of these guys will be heavier. I claim what I'm asking is something very different here. Okay? Now what I'm saying is as follows. What I'm saying is we have a collection of steers. We know their mean and we know their standard deviation. Okay, so here's their mean. What I want to know is, I want to know the weight that a steer would have to be in order to place in the top 15%. Now, obviously, to place in the top 15%, you could take something like 1,500 pounds. But what I'm asking for is the minimum weight that it would have to be. So what would have to be that weight in order to place a steer? Okay, notice now what we're given is we're given the percent or the areas, and we want to find our corresponding data value. Okay, essentially we're going in the inverse direction. And I'm saying the word inverse because that tells us how we're going to compute these. So when you're given the area or the probability and want your data value, you use what we call the inverse norm. Okay? The inverse norm, the way you enter this in your calculator is you put the area to the left, the mean, and the standard deviation. Okay? So, I will make the point though that some calculators are a little higher tech than what I have, and you can actually tell your calculator what range of area you're putting it in. My calculator, I always need to put the area to the left. And the other key thing you have to remember to do when you do that is it must be in decimal form. So, let's talk about this. We want this weight right here. And what we're given is that 15% are heavier. That's the area to the right. If we want the area to the left, you have to remember that everything is 100%. So you subtract off the area to the right to get the area to the left. So what we would compute here is inverse norm, and you'll see it right below your normal CDF. 0.85, 1,152, and then 84. And it turns out that the minimum weight would be 1,239 and 600 pounds. 600 really matters. Okay, so what if I wanted to know the following? Okay, instead of it being in the top 15%, suppose there's a steer and he's walking around and he's like, oh yeah, I'm in the top 2%. Okay, in other words, only 2% of the steers are heavier than this fellow is. What would be the minimum weight for him? Well, what we would do is we would put an inverse norm again. But now if 2% are heavier, that means he's heavier than 98% of them. And I don't mean to be sexist by calling it a him. So we'll put in 0.98, 1,152, and 84. So this fellow would have to weigh 1,324.51 pounds. All right, one more of these, just for completion purposes. What if I wanted to know what instead is the maximum weight a steer would have to be in order to place, in the bottom 5%. Okay, what would he need to weigh now? Well, notice now we're interested in the bottom 5%. Notice I say the maximum weight because I need to know that cutoff value. Obviously, if he weighed 2 pounds, he would be in the bottom 5%. Okay, so we want to find that kind of cutoff weight. Well, here what we would do, same idea. Notice we're given our area and we want to find our data value. Okay, now what's our area to the left? It's actually 0.05. I just wanted to do an example of that just to contrast that for you. So not that we really care, or perhaps we do. But this fellow would have to weigh about 1,013.83 pounds. Okay? While we're on the subject of these steers, one last question here. One last question I'll ask. according to the 68, 95, 99, 7 rule, and this distribution stated above. Let's do the middle 95% of steer weights are approximately between what two values? Okay, so notice we have 68, 95, 99, 7 rule. Recall 68%, the middle 68% lie within 1 standard deviation of the mean, 95% are within 2, and 99.7 are within 3. In this particular example, we're interested in the middle 95%. So what I do is I take my mean and I add and subtract 2 times my standard deviation. So what we'll see is that they're between 984 pounds and 1,320 pounds. All right, so just to summarize with our normal distributions, again, you can find the probability that you're within a certain region. And when you do that, you use your Normalcdf button on your calculator. When you're given your area or your probability and you want to find the corresponding data value, that's when you use your inverse norm. Okay? And last but not least, and actually the first thing that I introduced was the 68, 95, 99, 7 rule. Now I recommend you draw pictures of these normal distributions just so that you can get kind of a visual idea of what it is you're looking for. I can't emphasize enough the importance of drawing pictures in math. It just really helps you ask at the end, does my answer make sense? Thank you.